Natalie, you can still see my slides, the slides okay?
I can see it, and I just started recording.
Okay. Well, why don't you kick us off and we'll get started on time.
Okay, well, welcome to our webinar. We're going to be talking today about our Celeris system. With me on the presentation slate is Jeff Farmer, who is the CEO of Diagnosys. And we have as a guest presenter today, Adam Baker from the Ottawa Hospital Research Institute, who has, he just told us, been working with our systems for 17 or 18 years. And has been doing animal electrophysiology for about that long. So we're going to be talking today about just animal electrophysiology in general. I am muting everybody. Don't take it personally, but that way it will run a little bit smoother as Jeff and Adam talk. If you have any questions during the webinar, please don't hesitate to put them in a little chat bubble. What I'll be doing is I'll be monitoring that during the webinar. If it's a quick question, I'm happy to answer it. We will have a Q&A session at the end. So if it's a particularly good question, or if it's one I think everybody could benefit from, I'll hold it for the end for Jeff or for Adam. Without any ado, Jeff, you want to take it away?
I will. Thank you, Natalie. Thanks, everyone, for joining us. Good morning, good afternoon for those of you in North America and Europe who are joining us. Not sure that we have anybody from Asia, but if so, good evening. As Natalie mentioned, then I'll get us started with a couple of slides, and then I'll turn things over to Adam. Questions would be great. We'll leave 15 minutes at the end, but happy to talk about whatever topics and questions you have along the way, as Natalie mentioned. And we'll also be able to give you a copy of the slides afterwards if you send us an email, so happy to share them as well. Okay, to get us started, topics. So the main thing is Adam will be sharing with us his test data on a variety of Celeris protocols on both wild type and model animals in his presentation. And then we'll go through questions on that topic and then any general questions you might have about Celeris at the end. We have others from the Diagnosys team joining us, Rich, Anna Rosa, and from the sales support team. So quick introduction on Diagnosys. For those of you new to us, we were founded in 1984. We have offices just outside of Boston and Cambridge in the UK. And we've also set up an office in Dublin, Ireland as well. Anticipating the possibility of Brexit, we also have distributors around the world as well. So in North America and in Europe, the UK, we work and sell our systems directly with customers. And then typically in Asia, Australia, South America, we work with distribution partners. Before we talk about Celeris, I'll just quickly note that we do have animal testing systems that pretty much span the array from zebrafish through rodents, which is what we'll spend time talking today, up to larger mammals and non-human primates as well. Celeris itself is a product that we designed and launched about 4.5 years ago now at Arvo. We designed it to be compact, so this shows the entire system. There's a console, it comes with a computer and our software. The goal of the design of the system was to make this easy to train. We have probably about half of the customers in the United States, for example, that have bought Celeris had never done electrophysiology before, so part of what we're trying to do with the system was to make electrophysiology simpler to train, learn, and then operate, with the goal ultimately of having a very high throughput system and very high performance. And we'll share some of that data with you here today. We also have a wide array of tests that are possible on Celeris, and we'll talk about that during my slides and then Adam's as well. One of the key innovations with Celeris is how we designed the stimulators and electrodes. They're actually integrated together. So as you can see, let me switch back to the laser pointer. As you can see here, these are the full field stimulators on the right-hand side of the chart, and then the pattern stimulators on the left-hand side. In each case, the stimulator is part of this device right here. And so you can see we have a stimulator on each eye. And the electrode is a little bit hard to see, but it's right at the tip of the stimulator. It's a silver chloride electrode. It's circular, and it goes all the way around the output of the stimulator. So you've got, again, the electrode and the stimulator, monocular for each eye, or dicoptic, and integrated together. There's a number of advantages to that, and we'll talk about that next. Touch-touch protocols is a term that we use to coin protocols that only need to use the electrodes that are integrated with the stimulator. So probably 3/4, maybe 80% of the protocols that you can run on Celeris are touch-touch type. The big advantage of that is that no needle electrodes are needed. So that saves a tremendous amount of time in setting up the animal. It also tends to give much more repeatable results and lower noise as well. And you'll see that in some of the data. In addition to the touch-touch protocol, some other features of Celeris, we have a rapid ability to customize protocols. So if you buy Celeris or if you own a Celeris, you'll have approximately 15 standard protocols preloaded with the system, depending on which stimulators you bought with your system. And either yourself or our support team have the ability very quickly to create new protocols from any of those standards. And that's oftentimes the way we end up creating new protocols, is working with customers to change protocols to meet their exact needs. And a lot of those, if they're willing to share, are in the future then become a standard part of the protocols that we offer to all customers. We have multiple ways to export data, and the system itself is quite customizable. So I have a quick video here that demonstrates the concept of the touch-touch. Let me see, I'm going to need to get my other pointer back here, it looks like. I'll just play this. So this shows a touch-touch setup. Right now we are stimulating the right eye, so the active electrode is the electrode on the right eye, and the software automatically looks to the electrode on the left eye as the reference. So I think and now we have flashes on the left eye, and you can see a background light being put on the animal's right eye. So our protocols automatically will switch back and forth between eyes, stimulating one at a time, and automatically going back and forth between right and left electrode as active and referent. So we'll show you quite a bit of data from touch-touch, as well as some of the other setups you can use with the system as well. You go forward. So touch-touch has been shown generally for animal electrophysiology, and it's the same for humans as well. If we have the ability to use the fellow eye as a reference location, we tend to like to do that. It is a low noise location for a reference electrode, and also is very helpful from a repeatability standpoint. So data in the upper left-hand corner here, we show 3 or 4 tests that were done with the touch-touch setup. And then you also can use needle electrodes, and we'll show that on Celeris, but this is using a needle electrode as a reference, and you can see that the touch-touch protocol was able to achieve much better repeatability than using a reference electrode. The other pictures then show some of the animal setups, mice, baby mice, rats, and guinea pigs that our customers have used Celeris in their testing so far. High repeatability. We always recommend customers when they buy a system to do repeatability tests, or if they're testing us in a demo mode, to check repeatability. It's a really important attribute. So this just shows some of the repeatability data that we have in both cases for ERG, both dark adapted and light adapted ERG tests. And now a couple of charts on the full breadth of tests. Adam is going to go through most of these tests in his presentation, so I'll just mention this in passing. Again, for our system, we have full field stimulators as well as pattern stimulators, so that's one way to break up the test types that you can do on Celeris. This chart shows full field tests, both ERG, so you can see dark adapted, C-wave, light adapted examples on top. And then on the bottom, in the bottom left, we have a scotopic threshold response. This is just one response as part of a typical STR series that you can run on Celeris. You can also run VEPs. So in this case, bottom middle, we go a flash VEP response, as well as other types of ERG tests. So a PH&R, we have a standard PH&R protocol. And then finally, we have the ability to do UV stimulation as well. So I think, as everyone knows, mice have UV cones. So we have stimulators that are based on red, green, and blue LEDs, but we also have those that have UV LEDs as well. So you can use those to do dark and light adaptive tests. This shows some examples of tests that you can do using the pattern stimulator. So on the top, these are pattern ERG responses from a mouse, a rat, and a guinea pig. And then on the bottom, we have a pattern VEP test. So standard VEP setup with electrodes on the visual cortex and then typically in the cheek as a reference. And you can do then a VEP using either the flash stimulator, or if you have a pattern stimulator, you can also do a pattern VEP. I should mention in both cases, we also have protocols that you can do ERGs and VEPs together, either flash or pattern. So there's a lot of different ways you can combine protocols into different sequences, and in some cases, doing the test, a VEP and an ERG, for example, at exactly the same time. Depends on your test goals for your project. And then we're always working on new protocols. So one of the new protocols we've been working on this year with Adam, actually, and a couple of our other customers is a multifocal ERG protocol. This test result here is from a 7-hexagon. We've also been working on a 19-hexagon multifocal ERG, and we hope to have that optimized and released to customers with pattern stimulators later this year. And then I will not go through all of this, but this lists, as of today, the current set of protocols that we ship with Celeris. So when you buy one of our systems, our software upgrades, our general support, and any new protocols generally are all free that come with the system. We try and push these out to customers as we release new software and protocols, but if you haven't received, if you own a Celeris today and you haven't received a software update or new protocols from us in the last 6 or 9 months, feel free to contact our support team and we'd be happy to help you with either a software upgrade, or if you see protocols on this list that you don't currently have, happy to get those to you as well. And again, these map into the different types of stimulators that you would have on your Celeris. Regular RGB flash, we have different luminance levels, bright, standard, and dim. We have the UV flash stimulators in 2 different configurations, red, green UV, and then green, blue UV, and then the pattern stimulator that you can do pattern ERG VEPs, either monocularly, which is what most customers do today. We do have a few customers that have 2 pattern stimulators, and in that case, then you can run the binocular set of protocols as well. Okay, so that was a quick introduction to Celeris. I'll turn things over to Adam here in a minute. As Natalie mentioned, Adam has worked in this field for 20 years. He's used a number of different Diagnosys SPN systems over the years, and has been operating a Celeris unit basically since we launched it about 4.5 years ago. So a lot of experience working with Celeris. And Adam, I will turn things over to you.
All right, thanks, Jeff. Hope everyone can hear me okay. As Jeff and Natalie mentioned, my name's Adam. I am a senior research technician in a gene therapy lab at the Ottawa Hospital. General approach in our lab is a viral mediated delivery of the X-linked inhibitor of apoptosis, or ZIAP, to provide protection against disease progression. So a few of the diseases I've worked on over the years that we've had success with include RP, ischemia, retinal detachments, and glaucoma. And right now we're just finishing up a study on LHON as well. So today I'm going to be talking with you about a few of the models that we run in our lab, as well as the waveforms and biomarkers that are available with the Celeris system. But I'm going to start with animal preparation, which is pretty key for ERGs to get good, clean, repeatable traces. So with the majority of the protocols that Diagnosys provides, the mice need to be dark adapted, and generally 2 to 3 hours should be fine. Now, our lab, I bring the animals up the night before, we weigh them and prep our anesthetics. And if you have a ton of animals that you want to blow through, it's really nice to start as early in the morning as you possibly can. So as I mentioned, we dark adapted our animals overnight. and we probably run through about 18 to 20 animals a day. And that's because our testing takes about 20 minutes per animal for the 3 or 4 protocols that we're running. Now, the system is, sorry. It's terrible. So it's 18 to 20 animals per day at about 15 to 20 minutes per animal isn't super fast throughput, not for what the system can actually do, but for, like I said, the amount of testing we're doing, it's pretty quick. So now, oh, sorry, I skipped ahead of a slide here. Let me go back one. Sorry about that. Now, most of you are probably using some form of ketamine xylazine dosage cocktail to anesthetize your animals, or you will be if you haven't started ERGs yet. You're going to need to work out the best possible dosages to keep your animals under long enough to ERG. Even if the testing you're running is only 5 minutes, you still want the animals under a good amount of time so that they can reach a really solid surgical plane of anesthetic. That's really key for, again, repeatability with your tests between animals as well as the same animal if you happen to be ERGing him or her week after week. So for me, on a typical day, I'll run you through how I set up an animal. As I mentioned, they're dark adapted overnight. I'll inject my first mouse with anesthetic, and it usually drops within 5 or 6 minutes. I'll then give a drop of tropicamide followed by phenylephrine shortly afterwards. And again, these animals dilate pretty quickly, so within 5 or 6 minutes, the animal gets a ml or 2 of saline to keep them hydrated. I place them up on the Celeris table where at that point I'll give them a drop or 2 of topical anesthetic. I'll put the hypromelose solution or some form of a tear gel on the corneal stimulators and then slide them into place. So you want to make sure, again, when you're testing these animals that the cornea is always hydrated. Most people, I believe, are using a tear gel, which helps keep the cornea hydrated for the entire test, but some of you may be using liquid drops. Now, there's nothing wrong with liquid drops. They work well, but you're going to have to remember to reapply the drops throughout the testing to just make sure the cornea doesn't dry out. Now, all these steps I've just talked about are necessary to run, but when we have issues with our ERG system, there's really 3 areas that that I'll go to and check out the animal. The first is the level of anesthetic. Now, we've all done toe pinches in animals. That's really the best way to test whether or not your animal is at a good level of anesthetic to run the testing. If they're not deep enough, they tend to move about on the Celeris system. The second thing I'll check is dilation, which is very important. Obviously, if you can't get light into the eye, then you're not going to get a maximal response. And the third issue that people have sometimes is with the topical anesthetic. So topical anesthetic is going to kill any kind of a blink response that the animal has, any kind of muscle movements around the eye, either from the stimulators touching a lash or hair or something similar. That can create a lot of noise in your traces if you're not using the topical anesthetic. Okay, so all told, including hookup my animals, they are down or under anesthetic for about 15 minutes before I run the protocol. And then since I'm running so many animals and you want to keep the part going, I'll generally have my next animal anesthetized and ready to hop on the platform as soon as animal number 1 is done. All right, good, here we go. Okay, so there's a couple things you're going to want to watch out for when you're setting up your animals. And you can see pretty clearly in the top 2 pictures, you want your animal laid out nice and relaxed, not all hunched up like the picture in the top right. What a hunched up animal has problems with is they'll have issues with breathing, and the head starts to move, and you can introduce noise in your traces, and sometimes you can even lose contact with the corneal electrode. So with regards to the stimulators, and Jeff was talking about touch-touch protocol, which you can see the bottom left image, I always try to place my stimulators in line with the animal's visual axis. Now, what this does is it ensures good, even contact eye to eye. And you definitely want to make sure that you don't push the stimulators in to the eye with too much pressure. Too much pressure in the eye, obviously, if it lasts too long, you're going to increase interocular pressure in the animal, and that's going to cause a lot of, or it could cause a lot of interretinal damage. Okay, so now that my animal's basically prepped and ready to go, I'm going to run through with you fairly quickly the various waveforms that are available and what their biomarkers represent. These first few waveforms I'm going to talk about are all from a full field flash ERG. So what you're seeing here is a typical full field flash ERG. The majority of the protocols that are run will give you this type of waveform. You can see the first negative peak. Let me see if I can get that pointer going here too. Sorry about that announcement. As you can see here, the first negative descending wave, just a peak, it's called the A wave, and that's a direct measure of photoreceptor response. And then along the ascending wave, you see these spikes. These are called oscillatory potentials, and I'm going to talk about them a little bit more in the next slide. At the highest peak of the wave is where the B wave is usually placed, and the B wave is characteristic of bipolar cell and Mueller cell function. The B wave, just to let you know, is measured from your A wave all the way, or the peak of the A wave all the way up to the B wave. So it's always relative or relying on A wave. Okay, a bit more about the OPs that I mentioned, that you saw on the last slide. As I mentioned, these are generated on the ascending limb of the B wave, and through the use of filters, they can be isolated and measured individually. Now, if you look at the literature, OPs tend to be measured quite a few different ways. I've seen them measured from baseline up to the top peak. I've seen them measured from peak down to negative peak, where you can add separate markers, call it a negative OP1 if you want to. I've also seen them measured as area under the curve. Now, one thing I'm going to mention here is it doesn't really matter how you measure these biomarkers. We know there's no international standard for animals. And what I'm about to tell you is this applies for all the biomarkers. As long as you keep it standard within your own lab, across your students, within your own testing, then you should be fine for comparisons. All right, next up, we have what's called the flicker response. It's still a flash ERG, but instead of a single flash for response, a repeated flash is used at a certain set frequency. Now, this trace can be run at a wide range of frequencies, and the waveform is a measurement of cone function and cone opsin regeneration rate. All right, this waveform is generated from a photopic full field flash. You can see that it contains your negative going A wave, your positive B wave, but the component we're interested in with this flash is down here circled, the photopic negative response. Now, this is a measure of interretinal function, including ganglion cell activity. When you're taking the measurement, it's from the baseline, or which is your line coming across here, down to the photopic negative. All right, this next trace is a C wave response. It's still generated from a full field flash. Like Jeff had mentioned, 80% of the traces tend to be from a full field flash that we use on the Celeris system. So the difference with this wave is instead of a quick millisecond flash of light that most of the others were using, the flash is extended longer, and recording is longer as well, about 5 to 15 seconds, as you can see on the slide. So you still have your compressed on the left-hand side, you still have your A wave, and then ascending up to the B wave. And I guess what you could call the second ascending wave, at the peak of the second ascending wave, is where we place our C wave. And it's derived from the retinal pigment epithelium. All right, this negative wave, characteristic of a visually evoked potential. It's still generated from a full field flash into the eye, but we use a different active electrode to pick it up. I'll show you more about this later on, but you basically place an active needle electrode subdermal, horizontal to the skull, just above the visual cortex. The VEP provides functional information on the entire visual pathway, including conduction of signal along the optic nerve. And it's measured, again, like I mentioned, at the visual cortex. All right, the next two slides I'm going to talk about are actually generated by a pattern stimulator instead of the full field stimulators that we've been talking about. Instead of a single full field flash of light, the eye is stimulated with a reversing pattern of dark and light horizontal bars at 100% contrast. What you're looking at here is a typical pattern ERG, and P1 and N2 at the top positive peak and your second negative peak are measurements of ganglion cell function. Now, further, P1 is thought to come from the ganglion cell soma, and N2 is more related to ganglion cell axon function. This trace, this waveform is a pattern visually evoked potential, and as with the flash VEP that we talked about earlier, it's measured at the visual cortex again and provides a measure of function of the entire visual system. The biggest advantage, I guess, over with the pattern ERG over the flash VEP is that it's considered a lot more sensitive for your testing. So that's a quick run through the various waveforms that are available on the Celeris system. I'm going to give you a quick overview of the few tests that we run consistently in our lab, and then I'll talk about some of the models that we run in our lab as well. All right, this first protocol is a full field flash dark adapted ERG with oscillatory potentials. It uses only the two flash stimulators in what Diagnosys and Jeff referred to as a touch-touch setup. So both left and right eyes are run at the same time, but alternating flashes left and right, and then left and the right continued until the testing is done. The stimulator of the eye not being flashed acts as a reference to the test. So this protocol, as you can see, runs through three increasing intensities from 0.01 to 0.1 all the way up to 1 candela second per meter squared. And it's giving you measurements from the photoreceptors with the A wave, B wave with bipolar and Mueller cells, and then your OPs, you can extract Amakin cell data. We use this protocol. Doesn't matter if we're looking at the inner or outer retina. It's a really nice, quick little scotopic protocol that gives you quite a bit of information. All right, this next protocol is the simultaneous ERG and VEP. It's another full field flash ERG protocol. This one, however, is a single intensity protocol that uses the two flash stimulators on the corneas again, but it also uses a separate reference active and ground needle electrode to give you your VEP data. So as you can see with this protocol, we're getting measurements from the photoreceptors, the bipolar cells, the amacrine cells, as well as overall function of the visual pathway. So we run this protocol all the time if we're looking at intraretinal function, some form of ganglion cell disease or something like that. The next step, or this next protocol, is an 8-step intensity series, dark adapted again. It runs from the scotopic at 0.003 candela seconds per meter squared, all the way up to the photopic at 100 candela second per meter squared. The electrodes for this protocol are a little different. You still have your two touch-touch protocols on, or your two stimulators on the left and right eye, but this protocol needs an active reference, or sorry, a reference electrode in the mouth or subdermally in the nose, and a ground in the tail. The difference in electrodes with this protocol is mainly because instead of alternating left-right flashes within the animal, both eyes are stimulated at the same time and both responses are recorded at the same time. So instead of using one of the flash stimulators as a reference, we have a different reference, and they can both stimulate and record from the animal. And again, you get a measure of photoreceptors and bipolar and Mueller cells over a wide range of intensities. All right, this is the pattern ERG protocol. Unlike the full field protocols where both eyes are tested either simultaneously or alternating, with this protocol, one eye is tested to completion and then you switch to the opposite eye. Jeff showed you earlier, I believe, the pattern stimulator is positioned over one eye, and the second eye has a full field stimulator that acts as a reference. And again, instead of flashes of light, just as a reminder, the pattern stimulator uses alternating bars of light and dark to elicit a response. Now, if you're lucky enough, as again Jeff mentioned earlier, if you're lucky enough to have two pattern stimulators in your lab, then be able to run both eyes simultaneously, I'd assume. As I mentioned before, it's a direct measure of ganglion cell function. And again, we run this protocol with every inner retinal model that we work with. All right, this last protocol that I'm going to touch on is called the VIS pathway, or vision pathway, or visual pathway. It combines 3 different protocols all in one. The simultaneous ERG VEP protocol that you can see in the top 6 panels here, your flash ERG OPs and VEP for the right and left eye, as well as your C-wave protocol and your photopic negative protocol. Now, I don't use this protocol in the lab necessarily for the experiments we're running, but what I do use it for consistently is if someone from another lab comes to me and thinks they might have some type of a visual phenotype, I'll run this protocol through with a bunch of their animals, and if I see anything interesting, then I'll probably go with more sensitive protocol to check out what I happen to notice. So that was a look at the protocols that we tend to use in our lab, or the protocols that are most popular that we use in our lab. Now I'm going to show you a few of the ways that these protocols have helped with our research. So this first experiment, excuse me, I'm going to talk to you about is a bit older of a protocol from the Celeris that we used to use. It's still a touch-touch setup, and you can see the animal down in the bottom right. 1 electrode or 1 stimulator on each eye is all you need. This protocol has 4-step increasing intensity from 0.03 candela seconds up to 10 candela seconds. It's very similar to the 3-step dark adaptive protocol that I went over with you a little bit before, but you have a wider range of intensities, and it runs from scotopic to photopic. So early on, when we first started, or when we first got the Celeris, I guess, as Jeff mentioned, about 4 years ago, we had recently started looking at the inner retina. We wanted to do some really quick experiments to develop a model of ganglion cell death. Now, there were a few chemical inducers in the literature, and we decided on rotenone, mostly because it's well reported as a model for glaucoma, as well as it was reported that it should only affect the inner retina, the ganglion cell layer. So we injected the eyes, or left eyes, with rotenone, and we ERG'd at 1 day and 1 week. And what you're seeing here and what you'll see in the next slide is the 1 week time point. And you can see in the right eyes that are the red traces, everything looks pretty normal. Some really nice traces from the animal, good A waves and oscillatory potentials as you get into higher intensities. But in the left eyes, the signal is pretty much quenched. You can still see tiny A wave, tiny B wave, again, tiny A wave, tiny B wave, and then the A wave grows a little bit with higher intensities, but the signal is pretty much gone. So what this really means based on this test is rotenone does in fact affect the outer retina, which as you'll see in the next, I'll talk about more in a second. So after the 4-step intensity series that we ran the pattern ERG protocol. And again, similar results. You can see that the right eye, nice standard trace, good P1 and 2 values, but the left eye is severely reduced. Now, if this was based on the PERG alone, this would have been a great model for us. Again, it would have been solely a ganglion cell model. But since the outer retina is quenched as well, as I showed you in the last slide, we ended up not going with rotenone. And so the Celeris really helped us out with that, I guess. The second model I want to talk to you about is a model of optic nerve crush. One of our collaborators had been running experiments on the crush model for quite a few years, but had never really done any functional analysis. So we wanted to start using this model as well. We kind of traded off. We had them teach us the surgery, and we performed a bunch of surgeries and characterized the effects. So the first 6 panels at the top are from the simultaneous ERG VEP protocol. And if you have a look at the picture in the bottom right of the mouse, you can see the electrodes needed for this protocol now. You have your 2 stimulators on the corneas. This green electrode that runs across the mouse's back is your active VEP electrode. And once again, it's placed subdermal, horizontal to the skull above the visual cortex. And pretty important to keep it centered between the ears. This purple lead is our reference electrode, and then we have a ground electrode in the tail. Now this purple lead, and I believe Jeff mentioned, you mentioned this earlier, I'm not sure everyone uses one similar. What it is a gold loop electrode, and we find it pretty quick and easy to get this electrode into the mouse's mouth. We either place it on the tongue or in the cheek, someplace wet, and it acts as a really nice reference. Alternatively, you can use a needle electrode subdermal at the tip of the nose, and it works just as well. So the results of this model were actually quite nice, we think anyways. You can see back to the waveforms that your right eye, really nice traces. You have a nice flash A wave and B wave, the oscillatory potentials, and a really well-defined VEP. When you move to the left eye, you still have good definition in the traces and the flash as well as the OPs, but the VEP is non-existent or pretty much quenched. You'll also probably notice that the left eye is, the amplitudes are slightly lower than the right eye. And this happens sometimes with the surgeries, but not all the time. We had some animals that were even left to right, some animals that were a little weaker or a little stronger left to right. And that's kind of the nature of the surgery. It's a little bit of an invasive surgery, and you can actually cause some retinal damage if you nick something. So the bottom panel is a pattern ERG that we took at 12 weeks post optic nerve crush. And again, in red, the right eye, you can see a really nice ERG trace, really nice high pattern ERG. And in the left eye, the trace is somewhat reduced. Now, again, this is 12 weeks post-surgery. So for us in the lab, this is kind of what we look for when we're exploring a model. We would like a model where sometime a certain length after surgery, we still see some function from the cells of interest that we're looking for. So again, I guess this one would have been an ideal, or this one is an ideal outcome for us in that the ganglion cells are still functional 12 weeks later, and our lab would potentially try our gene therapy strategies to see if we could protect against ganglion cell function earlier on, as well as maybe recover some of the VEP. Excuse me for 1 second. Thanks. So the next model I'm going to talk to you about is a rat model of P23H photoreceptor degeneration. The traces you're seeing here are from a dark adapted intensity protocol. If you remember, it's the 8-step protocol that I talked about earlier that ranges in intensities from scotopic to photopic. I've just chosen to show you 2 of the traces here at 0.01 candela seconds, the lower trace, and 10 candela seconds, just to keep it looking a bit cleaner. One of the first diseases we worked on years ago in our lab was this P23H model. For those of you that don't know, it's characterized by within 4 weeks, the animal has lost about 50% of their outer nuclear layer. And by 20 weeks, the outer nuclear layer has maybe 10% of the cells left in it. Excuse me. So in 2007, we published a study showing the protective effects of our gene therapy with ZIAP in this model, and now we've recently come back to it. We're going to be looking at combination therapies. We have a novel antioxidant compound that we want to run on its own, as well as in conjunction with our ZIAP gene therapies to see if we can find any synergistic effects between the two. So as you can see in this top panel, wild type normal long Evans rat at 0.01 candelas, we have a nice trace, and then at 10 candelas, the A wave is really elongated, OPs have become well defined, and the B wave, again, is nice and high. At 20 weeks in the wild type, you'll notice that the traces are a little bit smaller, amplitudes are a little bit less, still very nice traces. And this is typical, and we believe it's from an age-related degeneration more than anything else. Now, if you come down and take a look at the P23H rat, again, at 4 weeks, the traces are reduced when compared to their age-matched wild types. But it's still a nice trace. You still have a decent A wave, you still see your oscillatory potentials, and you still have a pretty high B wave. Now, if you look closely at the A wave, you can see that it's about half as much in amplitude by eye, obviously right now, probably a little less than half as much compared to the 4-week wild type. Now, this wasn't a surprise, and as I mentioned, about 50%, by 4 weeks, about 50% of the outer nuclear layer is gone in these animals. But where you really start to see the disease, and one thing that we did all the way along is we were ERGing every 2 weeks, so we had a really nice cascade or degeneration waveform to present. But at 20 weeks, where the outer nuclear layer has about 10% of its cells left, you can see that the A wave is pretty much non-existent. There's no formation of the oscillatory potentials, and your B wave is severely reduced. So this is ongoing in our lab right now. We've characterized the disease at this point, and hopefully soon we'll be able to start doing our gene therapy models and the antioxidant compound. We just, as most of you have probably been delayed over the last year or so, that's what happened to us with this protocol. All right, the last model I'm going to talk to you about today is a magnetic microbead model of induced ocular hypertension or glaucoma. As you know, glaucoma is a retinal ganglion cell layer disease and generally does not affect cells in the inner or outer nuclear layer in the early stages. So we started off with this experiment as we always do. We take baselines of our animals, but in this case, we also took baseline interocular pressure measurements. Just to make sure our mice don't have any pre-existing retinal issues. So we used 3 different protocols, the 3-step dark adapted rodent, the simultaneous ERG VEP, and the pattern ERG in this study. The week following baselines, our animals were injected with either GFP or ZIAP virus in the left eyes. And 3 weeks following virus injection, we performed our glaucoma surgeries, which entails an injection of magnetic microbeads in the anterior chamber of the eye, and then a handheld magnet is used to move these magnetic microbeads into the iridocorneal angle. So control animals in this study received, instead of microbeads, received an intracameral injection of BSS. And what you're seeing on screen right now are the 4 groups we ended up with. So we have our GFP control, which obviously got our GFP virus and a BSS injection, our ZIAP control, which got our ZIAP virus and a BSS injection, our ZIAP glaucoma animal, which got microbeads and ZIAP virus, and our GFP glaucoma animal, which got our GFP virus and, again, microbeads. So with these 4 panels, you can see everything looks very similar, and in fact, there was no statistical difference between A wave or B wave values with any of the 4 groups. Similar to the waveforms in the previous slide, the amacrine cells, we had no significant difference with the OP values between any of our groups. And again, these last 2 slides we were looking, I'm just showing you one intensity, but the results were similar over all 3 of the intensities of the test. So this next slide is from the simultaneous ERG VEP test. It's a flash VEP. And again, you can see that all 4 groups appear similar. And it was the same with the flash waveform as well as the OPs with the simultaneous VEP test. Now, we were honestly a little surprised or maybe hopeful that we'd see some form of a reduction in VEP at this point, but we can talk about that a little bit later too. Now, the next test we ran, this brings us to our final test. It was the pattern ERG. And as you can see, the GFP, ZIAP control, and ZIAP glaucoma groups all have similar amplitudes. There was no significant difference between any of these 3 groups. And in comparison, if you look at the GFP glaucoma animal, it showed a significantly impaired RGC function. And in fact, P1 was reduced by about 43%, and N2 was reduced by about 31%. So in this study, it suggests that our ZIAP gene therapy is protecting ganglion cell bodies from a loss of function due to elevated IOPs. Okay, well, that's it for the models that I was going to talk to you about that we've used in our lab. Just a couple final words. I've taken you through the prep and animal setup, which is key, the types of data that the various biomarkers and protocols can provide, and a few of the uses our lab has with the Celeris system. So just to summarize those uses, we use it as a means to determine whether an existing model would be useful to pursue, as with the Rodent model. We've used it to characterize new surgical techniques for us, which was the optic nerve model. We've also used it to follow disease progression, again with the RP model I showed you. And finally, but most importantly for our lab, the system enables us to determine whether our therapies are providing a functional protection in our animals. So just to finish up real quick, I'd like to thank the team at Diagnosys for all your help over the last, like I said, 18 years. And for asking me to present here today. Thanks, everybody.
Adam, thank you. Fantastic job. I learn many things every time I hear you speak and go through the test data with you. So fantastic. Let's do this. Natalie, let's just start off and see if we've got any questions that have come in so far. And if so, let's hit those first. And if not, I've got a couple of questions for Adam. But Natalie, you want to lead this?
Yeah, we have a couple of questions. One thing that I want to mention before we get into the Q&A portion is that at one point Adam mentioned that there's currently no ICEV standard for animal testing. ICEV refers to the International Society for Clinical Electrophysiology of Vision. It's a group of big nerds like ourselves who actually set the standards for these kinds of tests. There's an annual meeting. The meeting was actually last week. It was virtual for the first time in ICEV history since they've been meeting in the 1960s. And at the standards meeting, there was a lot of interest. Somebody brought up the need for animal testing standards, or at least minimum standards, and there was a lot of interest. So while it's not currently, while Adam's correct, there is no standard and it doesn't appear to be currently in the offing, among the committee members and of the standards committee and among the attendees, there was a lot of interest. So that may be something that will be there in the future. So Adam, oh, sorry, Jeff, go ahead.
I was just going to say that's a fantastic point, Natalie. And why don't we commit to letting all Celeris customers know if ICEV does start that process, so that we can get anybody's input from our Celeris user group into that process. ICEV always welcomes it, as we know, and we can certainly get our customer base involved in that process as well. Very good point.
Yeah. So the first question we got. Adam, you mentioned topical anesthetic, and the request was if you could talk a little bit more about that, since most of the protocols for rodent ERGs you find available don't mention it at all. So.
Yeah, sure. I guess I first noticed it when we first started ERGing. We were always ERGing rats, and a blink reflex in rats is very noticeable. We would give a drop of a topical anesthetic. In our case, we're using Alkane. Touch the electrode to the eye, and the animal would start blinking. Within a couple seconds of giving a drop, this blink reflex would go away. Now, it's not so obvious in mice, but I think especially lately we've seen some traces where we get some noise, and that noise we think is attributed to the same kind of blink reflex or muscle movement around the eye, jumping the stimulators a little bit. Yeah, so yeah, we use it in all our tests. I think it's not necessarily called for in all the ERG testing, but we definitely give every animal we test a topical anesthetic.
Yeah, and to add on to that, it may not be as obvious, particularly in mice, in the shorter responses where, like ERGs, but certainly ripple effects from any muscle movements you can also see it's being more disruptive, possibly in longer recordings, like C waves or DC ERGs, where you're recording for several seconds at a time. And then another question, if you could provide any additional tips or tricks for good electrode placement, particularly working with young rodents. Tiny mice have tiny eyes, And so electrode placement can be kind of tricky to do practically, even though it's much easier now with the Celeris. It's still not the easiest thing it could be. And I know some labs cut the eyelids of the animals, but that's really something that everyone would prefer to avoid if possible. So if you could give any advice to our listeners on how to put the electrodes on the eye and how best to do that, that'd be helpful.
Sure. So we've gone as young as 5-week mice pretty consistently. Their eyes are pretty small, but we're still using the standard electrodes, the 3 mil electrodes that come with the system. If you're having trouble with smaller eyes, you really don't want to be touching the eyelid. The Celeris itself has a swingable light on it, a red light overhead of the animal. Don't be afraid to move that around, get it down right low into the animal where you can see the reflection off the cornea. Another thing I do in the lab in the dark is I have a headlamp on, and that lets me get right up close to the animal. It's a red headlamp, and I can really see the corneas quite well. And with the full field stimulators, it makes it a lot easier if you can see the cornea to get them centered and attached. Yeah, it can be difficult, especially with super small eyes, but again, try and get them centered, try and have them pointed in the same direction. It's not as critical if they're slightly off the center axis of the animal with the full field stimulators, but you want to try and keep them as standard as possible. Does that help?
Yeah, that's fantastic. So then the next question, I want to toss over to you, but I want to talk about it for 1 sec before I do, Adam. We have someone who's asking about normalizing responses and also a little bit about placement, I guess, because they're seeing variation between right eye and left eye in wild type animals. And so one thing I would suggest, if you're consistently seeing differences from your response from what you're expecting, there are only 3 possibilities. One is that it's the equipment, one is that it's your animal, and one is that it's your procedure. And the easiest way to tell if it's the equipment that's causing the problem is to take these stimulators out and swap them. So if you're always seeing the right eye is lower, the right eye is lower, the right eye is lower, the way to ensure that you don't have a problem with your right eye stimulator is to unplug the right eye stimulator and swap its position with the left eye. If that fixes it, then give us a call. We'll start the process of recalibration for you. If not, then it's either your animal, which is more likely to be the case if it's just one animal and not all of them. Sometimes you have animals that you would expect to be normal but aren't. That's just kind of how mice go. But if you're consistently seeing it where there's constantly a difference between the 2 electrodes, then that's unlikely to be the issue. The third possibility is your procedure. If you're constantly seeing a difference between the 2 eyes, check placement. If it's always the right eye that's lower, for example, is that because of how the electrode or how the Celeris is positioned on the bench and you're having trouble reaching to the right eye, but not so much the left eye, or vice versa? If it's not always the same eye, is it possible that instead of being on the eye, the electrode is being placed above it or below it or on the cheek instead of going into the eye? So I would check your procedure. It's also possible, procedure being more of a global term, if, again, the right eye is always lower, where is your safety light in the room? Where's the light that you're using to inject the animal? Is it closer to one side than the other? Do you have it on the whole time? Are you turning it off after you're setting up the animal? So that would be another thing I would investigate. And then I would turn the rest of that question over to Adam and see if there's anything I missed on that.
I think you covered everything pretty well. One other potential issue if you have a weaker eye consistently is check the light sources in the room. If there's even something as simple as a green light coming off a monitor can light adapt one side of the animal versus the other. As for normalizing, we tend not to normalize our animals. We have in studies in the past where we have had well, actually, the RP rat model that we used to work on, we ended up normalizing to the point where our injected eye versus our uninjected eye, we would be looking for a ratio greater than 1, and that showed protection. A ratio less than 1 showed no protection, and at 1, the eyes were equal. But as for normalizing the animals, no, we don't really do that at all. If you're not talking about huge differences and you're not talking about a consistently always left or always right eye that is seems to be reduced, and that can just be the animals themselves as well. I mean, they're like us. They can have differences left to right. And your hope is that when you do enough animals, those small differences will be averaged out in the statistics.
Okay. Next question, we had a question about what the impedance value is. The impedance value basically is looking at the resistance between the electrodes and the animal. So basically it's giving you a general idea of how well you've hooked up to the animal. Typically what we try to do is I recommend trying to get impedances of about 7 to 15. Adam, would you say those are about what you aim for?
Yeah, definitely. Again, if it's around 15, what it really does is kind of introduce noise into your traces. So you want to keep them as clean as possible. So higher isn't necessarily that it's not going to work, but yeah, I definitely try and keep them within. I got a quick question for you, Natalie, but I don't think this has been done yet. We've never changed the color associated with the impedance values on screen yet. Have you? Or
we have not. That is something that we've introduced in the latest build of software, is that you can adjust what the green, yellow, red intensities are. My preference is actually to not mess with them too much, just because in general, the idea is that green is best and yellow is borderline and red is poor. But if you put a red filter over the screen, then green becomes impossible to read and yellow and red become approximately the same color. So I don't think it's in rodent testing, when it's so important to have no light leaking into the room ever. I haven't really made a point of adjusting those numbers.
yeah, and the numbers you gave are fine, and even lower as well. It's not something that I really concentrate on. I generally use the impedance check to make sure the electrodes are hooked up and nothing's failing. Short of that, I'm not really concerned too much with the numbers.
So the next question is kind of a big one. So it may be tough to grapple with, but how do you choose the intensities in protocols? Like, how do you know what to test for? And I think that's really a question that the ICEV standard for animal testing, should it come out in the future, would really be useful. But I think that your presentation really helped with, Adam. If you want to speak a minute for that. We don't have a ton of time. We do have 2 or 3 more questions.
Yeah, that's a good one. It's what you guys designed. No, I've changed some of the protocols around. It depends what you're looking at. If you want to look at just scotopic values, then you can gear your protocols to that. And if you want to go, I think the 3-step that I showed went up to 1 candela, but maximum scotopic in a mouse is what, around 2 or 3. So you can change intensities to get the maximum scotopic value if you wanted. If you wanted to look at photopic values, same thing. You would change your intensities to the higher intensities. It's more, I think, about what you want to get out of your data set and what you want to see or what you're potentially testing for in the animal.
So let's see, then at bright lights, starting at about 1 candelasecond per meter squared and higher, my traces don't start at baseline. The left and right eyes tend to start different distances away from baseline. How can you prevent this from happening during your recordings? Sophia, I think what I would do is so this I think is something that we could talk about more in terms of protocols. What you can do is you can adjust baseline subtraction and baseline drift options in protocols themselves. So what I might have you do is shoot us an email at support@diagnosysllc.com. I'll put that in the in the chat. What we can do is maybe have you send us one of those tests and we can talk about different ways to adjust it. But nope, I just sent that to somebody individually. Sorry, my bad. What I would have you do is just shoot us an email and I can see if that's something that we can address. And then another question we have is, Adam, again, do you have any tips for placing the reference electrode for VEPs, or I guess both the active electrode on the visual cortex and the reference for VEPs in as standardized a way as possible?
Yeah, so again, I'm going to assume most of you are using the needle electrode as a reference for the VEP, because I'm pretty sure that's what gets shipped with the system. It's a hard one to get in there. There's obviously not a lot of skin you can pinch to slide the needle in. I'll go as slow and I'll get down as close as possible and just watch the tip of the needle as I put it subdermal at the tip of the nose. Like I said, that's a hard one to get in though, and I think that's why we actually went to a reference electrode in the mouth for the VEP setup. Much simpler just to be able to put it in the cheek or on the tongue. For the VEP active electrode, that one I'll tend to grab the skin between the ears. I'll line the needle electrode up centered between the ears and push it in gently forward. Again, just subdermal, horizontal to the skull. It doesn't take a lot of force to go in. That's really how I do it. You want key points though, keep it centered. You want the tip of the needle so that it's actually past the ears once the needle's subdermal all the way. But yeah, the easiest way I find for that one is lift the skin behind the ears and push the needle in.
Do you get the same ERG for GFP transgenic mice as control mice?
GFP transgenics, yes. GFP virally induced, not always. Sometimes, again, our subretinal injection, if we happen to be going to the outer retina, we can cause a little bit of a damage. So compared to a control uninjected mouse, the traces are somewhat reduced.
Do you also use pattern VEP? I know there was one of the slides that showed a response from the pattern VEP, but in your models, you only showed flash VEP responses.
So we do. The pattern VEP protocol is fairly new, and the studies I showed you were already ongoing before that protocol became available for us. So that's really why I didn't show any of the models that we've used. But we are using it right now. I believe I mentioned that we're just finishing up with an LHON study, and we've used it pretty consistently for that study from start to finish.
Can we switch the reference line needles for VEP but put them in the right holes? It's hard to tell the color in a dark room. The needles are electrically exactly the same. There's no difference between one or the other, as long as you've got the one in the back of the head going to the right port on the Celeris, and the one in the reference going to the reference port on the Celeris, then it's fine. One thing that might be helpful is just to take a black Sharpie and scrawl on the length of it just to make it to make them more visually distinct, either to add dotted lines to it or.
I don't know if you can do this or not, Natalie, but this says head.
Yep. So Adam has marked his with tape, so you can certainly mark them. The needles themselves are totally identical. So the only difference is the coloring, and under red light, things that look very different stop looking very different. So I understand completely. What we try to do is send out needle electrodes that are maximally contrasting under red lights, but there are only so many colors we have to work with, and that's not always possible. So with that, we're about 5 minutes over. You guys had some really great questions. Thank you so much for attending and for such great questions. We did record this. We will be putting up a private link to this on YouTube, so we'll send that along to you guys as soon as we can. And very glad, Brittany, very glad that this was very helpful. Thanks again for attending, and if you need anything else, let us know.
Before we close out, Natalie, let me say just one more thing. As Natalie mentioned, we do have another set of Celeris webinars next week. It'll be the same topic, so you can pick the date and time that works best for you. Natalie and Anna Rosa from our Europe team will be going through Celeris protocol creation and data export. So those are on the 29th of September, either in the morning here in the US or in the evening. Pick your time. Those should both be very informative for both current customers of Celeris and potential users. And then I'll just close out with this again. In addition to myself and Natalie and Adam, we've had Anna Rosa and Rich Camara on the line with us as well. So if you have any follow-up questions for us, feel free to shoot any of us an email. John and Anna Rosa, as well as Rich's email addresses, are listed on this last page. Happy to give out the PowerPoint if you'd like to get a copy of that. And I'll just finally say, Adam, thank you again for preparing all of these slides and taking us through them today. Very, very informative and very much appreciated. Thank you again.
Thank you, Jeff.
You're welcome. All right, thanks, and have a great day, everyone. Bye-bye.
You too, Jeff. Have a good one, guys.
Bye-bye.
Bye.
See you Thursday.
See you Thursday.
Yeah.